More of the same stuff. Just some algebra identities or concepts, and then some equation stuff. So.
Okay. What do you got?
The first one is 1 plus x minus x squared, all raised to the power of 2.
I want you to simplify that, or just come up with an answer, or?
Simplify.
Okay. What we have is a trinomial. 1, 2, 3 terms. So we're going to multiply a trinomial by itself. So this is really what we're doing. Now do that term by term. And always try to follow the same pattern when you do these. Don't jump around. You know you have to multiply every term by every term and add them all together, but do it in an orderly fashion.
Okay.
The first term.
1.
Second term.
X.
Keep going.
Minus x squared plus x.
Hold on. Okay, sorry, my mistake. Go ahead.
Plus x squared.
Uh-huh.
Minus x cubed.
Okay.
Minus x squared. Minus x cubed. Plus x to the 4th.
Good. Now all we have to do is simplify that. Well, let's start with the highest degree. There's only one of those. And then let's cross it out because there's 9 things up there. It'd be really easy to make a mistake. How many x cubes do we have?
Negative 2.
How many x squareds do we have?
Negative 1.
The x's?
2x.
And there's always, usually there's only one number. There's only
Right.
one of those and there's only one of those at the ends.
Right.
So you don't have to search real far. So that's the answer. That's what they're looking for. Okay, what else?
9b minus 6.
9b minus 6?
Yeah, over 3b. And simplify.
Okay. Gonna call you?
I'll run it.
It's amazing. Okay. I would love to have somebody who knew technology explain that to me.
Yeah, that's really weird.
All right. Usually when I'm looking at a single denominator, I want to split it up into 2 fractions. In other words, I want to split it up into that fraction, and I want to split it up into that fraction. What does that give you?
9b over 3b,
which is
minus 6 over 3b.
All right, I'll write it like that. Now simplify that.
This becomes 3 over 1 minus 2 over b.
I would assume that's the answer they're looking for. That's the only answer they could be looking for. Okay. What else?
I have one question about that problem.
Okay.
So obviously there's different ways to do different problems. So if I kept it as one fraction and made the numerator 3 times the quantity of 3b minus 2.
Okay, well, let's go back. No, I know exactly what you're saying. I was thinking of that when I was doing it. In other words, I'm going to factor out a 3 from the numerator.
Right.
And I'm going to still have that. So the 3's would cancel, and that would be an acceptable answer. Notice that that's the same answer that we have. If you find a common denominator, that turns in, hold on a second.
It should be
3b over b minus 2 over b, which is 3b minus 2 over b. It's not the same. What did I do? That is, I didn't factor it right. 3b minus 2, the 3's still cancel, and you could have an answer 3b minus 2 over b, which is the same as what I have circled on the right.
Oh, right, okay. Gotcha.
Okay, that's the only difference. I don't even know of a mathematical convention that favors one over the other. I suppose maybe that would be the favorite because it's a rational quotient as opposed to a whole number minus a fraction.
Okay.
But like I said, there's no way any math teacher should take off points for one answer over the other, although if it's like a multiple choice test, you may only be looking at one of those answers. So you have to know what answer is the same as what another answer.
Okay. Okay, so the next one has a lot of fractions.
Okay.
On the numerator, it's 1 plus 1 over c minus 1. And then the denominator is 1 minus 1 over c minus 1.
Always handle these separately. Do that first. What does that become? In other words, when I mean separately, it does not matter how complicated the numerator is. Handle the numerator as a numerator and produce a single rational quotient for it.
C minus 1 over c minus 1 plus 1 over c minus 1.
What's that equal to?
C over c minus 1.
Alright, so now we have c over c minus 1 all over, and now let's do that one. So that's going to be c minus 1 over c minus 1 minus 1 over c minus 1. What does that equal to?
C minus 2 over c minus 1.
So I'm going to write that down there. Now, the safest way to do this problem is to flip In other words, now that you have the denominator as a single rational quotient, you can flip and multiply. And notice what happens. The c minus 1 disappears. So if I have a fraction in the numerator and I have a fraction in the denominator, and their denominators are the same, I can just cross them out. And I end up with c over c minus 2, which is the same thing that happens if I flip and multiply. In other words, if I multiply this thing by c minus 1 over c minus 2, those cancel, and I end up with that.
Right.
So it's a bit of a shortcut to do it the way I did it the first time. The only thing is that make sure you don't ever do it if the numerators are the same. If I have a over b divided by a over c, that is not b over c.
Okay.
Okay? If I have a over b plus d over b, then that is a over d. Yeah, in other words, if it's my denominators that are the same, I can just cross them out and deal with whatever's left. But if it's my numerators that are the same, then I have to flip everything. But the real secret to this problem is to do everything separately. Start there. Solve that. Come up with a single rational quotient like that.
Okay.
Then you can do stuff like, in other words, until I solve for a single rational quotient for the denominator, I can't really flip and multiply.
Right.
So I got to do that step first.
Okay.
All right. What else?
So this one's more fractions.
Okay.
So 1 plus 1 over 1, and then in that same denominator, it's plus 1 over 1 plus x.
Okay. Just this?
Yeah, just that.
Okay. Always work from the inside out. So that's the first thing we're going to solve. What's that equal to? What's that equal to?
1 plus x over 1 plus x plus 1 over 1 plus x.
Which is?
X plus 2, or 2 plus x, whichever. X plus 2 over x plus 1.
Alright, so now let's rewrite it. We have, because we have a single rational quotient in the denominator, we can flip and multiply. So now what do we have?
1 plus x plus 1 over x plus 2.
Okay, now solve that.
So x plus 2 over x plus 2 plus x plus 1 over x plus 2
Equals?
2x plus 3 over x plus 2.
There's your answer. In other words, it does not matter how complicated they make this. I've seen problems that are like 1 plus, when you were reading it to me, I wasn't sure how many steps we were going to go. You could basically go forever. And it does not matter. You start from the inside and you work your way up.
Right.
As long as you do it that way, then you'll never be dealing with anything more complicated than that. And you know how to do these really well. So just, it's like nested parentheses.
Right.
If, I can't even think of a good example, but it's a little bit like if I have 3 to the 3 to the 3, how do you do that? Do you do from the bottom up or do you do from the top down? There are no,
top down.
exactly, there's no parentheses there. So that's 3 to the 27th, which is 7 trillion. If I had 2 to the 2 to the 2, that's 16. It's amazing to me that that is a true statement. But it's, you work, when you have exponential, multiple exponentials like this, without parentheses, you work from the top down. Now, it's a different story if I have parentheses. If I put parentheses around that, then that's equal to 3 to the 9th, which is not that big a number.
Right.
But, so the parentheses make all the difference in the world. What else?
Okay. So this one is x to the negative 1 plus y to the negative 1 over x plus y in parentheses to the negative 1.
Okay. Let's convert everything to positive exponents and then see what we're looking at.
X plus y over...
No, I can't do it that way. You have to deal with that alone. And you'll see why in a moment.
Okay.
What's x to the minus 1 equal to?
1 over x. Right. Okay.
Now, let's solve that. Turn it into a single rational quotient. That's
y plus x over x times y.
Okay. So that's our numerator. And then our denominator is what?
1 over x plus y.
Well, that's already a single rational quotient. So I can flip and multiply. So now I have y plus x over xy times x plus y over 1, which almost makes me think I made a mistake because it would be really nice if that was in the denominator. But it's not, so the answer is x plus y squared over xy. That equals that.
Okay.
Now, yeah, no, that's the only way to do that problem. You can't even make it simpler. In other words, I can take this term and move it to the numerator, but I cannot take that combined term and move it to the denominator until I've turned it into that.
Right.
You have to turn these things into, when I say a single rational quotient, I mean a term in the numerator divided by a term in the denominator. Not something like 1 plus 1 over x over 1 minus 1 over x. That is not a single rational denominator, nor is it a single rational numerator. I have to turn it into those before I can advance on these problems.
Okay.
Okay.
So next one is x to the negative fifth times y cubed times z to the 10th.
V as in Victor?
Z as in zebra.
Zebra. Okay.
All raised to negative 3/5.
It's the first step.
Make x to the negative fifth 1 over x to the fifth.
Probably not.
No?
No, I think that's going to complicate things.
Okay.
The best step is to apply the rule of exponents when you're doing double exponentiation. If I had 2 to the 3 and I took it to the 4th power, what would you do? You would multiply them, right?
Right.
So do that here.
Oh, okay. Right.
Because some of these negatives may turn into positives. So what do you get with the x term?
You get x cubed.
What do you get with the y term?
It's raised to the negative 9/5.
And the z term?
It is raised to the negative 6th power.
Now, usually they do not like negative exponents in answers. So give me that answer with all positive exponents.
X cubed times 1 over y.
Well, instead of times, let's just draw a fractional line and put the y down there.
Okay.
What's the rest of it?
Z to the negative, or z to the 6th.
In the denominator.
In the denominator. Cool.
There's your answer.
Sweet.
Okay. Notice that had we done it the other way, it would have gotten complicated pretty fast. Yeah, because it would have been 1 over x to the 5th, and I'm taking that to the negative 3/5 power. That's a lot more complicated.
Yeah.
So the best thing to do when you see double exponentiation, do that first.
Okay.
And you know what I mean by double exponentiation, right?
Yeah.
Okay. It's actually not double exponentiation. This is double exponentiation. This is actually single exponentiation because that's 27 to the 3rd power.
Right.
I call it double exponentiation just because people know what I'm talking about when I say that. It's technically not, but go ahead. You know what I mean when I say that.
Okay. So this next one is the 4th root of the fraction on the inside, and the numerator is t to the 1/2, t is in Thomas, times the square root of 5t. And then the denominator is 5 to the power of 2/3.
Power of what?
2/3. I'm sorry, my allergies hit me like a brick wall a couple days ago.
No, I feel you. I've been suffering from allergies for a month and a half, and it's finally letting up for me. And I am so thankful because I've been so tired of taking Claritin every day.
Yeah, I woke up on Sunday morning and my throat was really scratchy and my nose is...
No, I know exactly. Yep. We might suffer from different allergies, but the last month and a half, lots of pollen in the air.
Yeah.
So, have I written this correctly?
Yes.
Okay.
Yes.
what's the first thing we want to do?
I'm not sure.
Get rid of the radical signs. You will find that radical signs don't serve a very useful purpose in math. They really don't. The higher up you go, in fact, this is probably the last year that you'll be confronted with, and you'll get radical signs in calculus, but you'll learn very rapidly to convert them to fractional exponents. Because everything in math that's higher than where you're at now depends on exponents, not radical signs. So anytime you see a radical sign, you convert it to a fractional exponent. So what's the first conversion here? Let's do it one step at a time.
The square root of 5t can become 5t in parentheses to the power of 1/2.
Okay. Denominator is still 5 to the 2/3. And what's this whole thing to?
The 1/4.
See, now I have it so it's real simple. Now it's just a question of multiplying. I got a bunch of double exponentiation going on, right?
Right.
So first of all, let's just distribute this second exponent to everything. What do you get?
T to the 1/8 times 5t to the 1/8. And then the denominator is 5 to the 1/6.
Okay. Now, I can do some simplification here. Notice that everything is being multiplied. There's nothing being added or subtracted. So t to the 1/8 times t to the 1/8 is what?
T to the 2/8, or 1/4, sorry, T to the 1/4.
So I have the 5 to the 1/8 times t to the 1/4. That's my new numerator. All over 5 to the 1/6. Now, what can I do with that?
Can you simplify the 5s without changing the exponent?
Well, here's what we're looking at. 5 to the 1/8 divided by 5 to the 1/6. What do you do with the exponents when the base is the same and the bases are being divided?
You can divide the...
You subtract. You never do the same thing. That's kind of the one thing you have to remember, is that you never do the same thing. I'm never dividing 1/8 by 1/6 because I'm dividing 5 by 5. So I always have to do one level less. So what that really is 5 to the 1/8 minus 1/6. Subtracting exponents. Now, that's equal, 24, I think, is my common denominator. So I have 5 to the negative 1/24. What's my final answer going to look like over here?
It's going to be t to the 1/4 over 5 to the 1/24. Right?
Good. And that's as simplified as you can really make it.
Okay, so when the bases are different, you can't do anything with the exponents?
Exactly. You cannot do anything with the exponents unless the bases are the same.
Okay.
Now, there's a couple of things. if the exponents are the same, and the bases are different, that's the same as 2 times 3 to the 1/2. So sometimes you can do stuff if the bases are different, but only if the exponents are the same. If I have 2 to the 1/3 times 3 to the 1/4, that I can't do anything with.
Right.
You have to have either the bases be the same or the exponents be the same. One or the other.
Okay.
Then you can simplify.
All right. Okay. Sorry.
That's all right. You have, I assume you have some review material that you're reviewing and trying to figure out which ones to present?
Yes. I have a session scheduled for tomorrow evening as well.
That's correct. At 7, right. Mm-hmm.
I'm trying to cover absolutely everything.
That's fine. Yeah, no. No, by all means, choose the toughest problems you can find. Let's go over those and prioritize it that way. Because you know pretty much the medium ones. I know you know all the easy ones. You know most of the medium ones. It's only the hard ones that give you any difficulty.
Right. Okay. So this next one, it's an equation.
Okay.
And it is x cubed minus x squared, and that's in parentheses, plus 2x minus 2 equals 0. And solve for x.
Let's take away the parentheses for a moment. Because clearly they don't do anything. Do you see why they don't do anything?
Yes.
I certainly don't need the first set of parentheses, and because that's a plus sign, I don't need the second set of parentheses. In other words, that's the same as what you gave me. Now, the reason they put parentheses around it is because this is one of the very rare cubic equations that can be solved easily using grouping. Very few cubics lend themselves to grouping. What has to be true for you to be able to group these is the ratio of these two coefficients has to be the same as the ratio of those two coefficients. Are they the same? Excuse me, yes they are the same. All of a sudden I was starting to wonder, what in the world are they giving you here? So, since that's minus 1 and that's minus 1, they are the same. And that means that it lends itself to grouping. Once you've grouped it by putting parentheses around it, now you can factor out the greatest common factor. In the left, what do you get?
X squared times x minus 1.
And if you've done it properly, do the same thing on the right.
It's 2 times x minus 1.
As long as that is the same as that, you've done it correctly. If they are not the same, you've made a mistake. Trust me. Now, take the greatest common factor out of that expression. What do you get? Still a factoring problem. What can you factor out of that?
Oh, x minus 1 times x squared plus 2.
Exactly.
Okay.
And there's your answer. Now, that gives me solutions of x equals 1, or x squared equals minus 2, which would mean x equals plus or minus the square root of 2I. So there's your 3 answers.
Right. Yeah, the cubic. Okay.
Okay, now let's go back a step. That's the way you do those. There's only one possible point of error. That's if that's a minus sign.
Oh, then the ratio is not the same.
Well, no, then the parentheses matter.
Oh, okay.
Okay, let me start this out properly. If that was the problem, well, this ratio is still 1 over minus 1. And this ratio is still minus 2 over 2. So the ratios are the same, right?
Right.
But I can't just add parentheses without changing it. In other words, I can certainly add those parentheses. But if I were to do that, that's different. That's not what I started with. What this becomes is x cubed minus x squared minus 2x minus 2. That's not what I started with. Let me erase those parentheses. That's what I started with.
Okay.
So you got to be careful about adding parentheses. In other words, you can always add parentheses at the beginning, pretty much. But if I'm going to add parentheses over here, I got to make sure I don't change anything.
Right. That's the same math.
So it actually becomes 2x minus 2. Now it's the same as what I started with. I haven't changed anything. And when I factor out the greatest common factor, I still get an x minus 1 there. I factor out a 2, I still get an x minus 1 there. Now everything's copacetic. And what's the next line?
Okay. Right.
What's the next line?
X minus 1 times x squared minus 2.
Now, can I go any further?
Okay. Yes.
Yeah, that's not imaginary solutions now on the second term.
Yeah.
So use difference of squares to solve that. It does not have to be difference of perfect squares. Difference of squares always works. I don't know why they called it difference of perfect squares ever. I suppose that's what they do when you're in 9th grade. But
yeah,
once you get to a certain point, you realize that it doesn't have to be perfect squares. What's x squared minus 2 factor into?
X plus root 2 times x minus root 2.
Now you have all 3 solutions.
Okay.
And they're all real.
Right.
They're not any imaginary solutions. So, that's and I will be upfront with you, 95% of my students would make a mistake on this problem. Because their first step would be to just add parentheses. In other words, they would do this. And you've just changed the problem. It's no longer the same. So pay attention to that. If it's negative, be careful. If it's positive, you don't have to be careful.
Right.
You can just add the parentheses to the 2 left terms and the 2 right terms, and everything's going to be fine. But if it's a negative sign, be very careful. Make sure that every row is the same as the previous row. That's the secret. Whenever you're doing math, and I'm not just talking about this problem, I'm talking about pretty much any time you're just manipulating a function. In other words, you're not trying to change it, you're just trying to put it in a different format. Well, just make sure you do not change anything from row to row.
Okay.
What else?
Apologies.
No need.
Okay, so
I've been on the other end, where I've been like you are, having to tutor, and boy, that is miserable, let me tell you.
Yeah, I can't imagine. I'm not having very much fun right now.
No, you're on the easy end. Go ahead.
So the next one is another simplification problem.
Okay.
It's x squared plus x minus 2 over x squared minus 3 plus 2.
Whoa. X squared minus 3 plus 2, like that?
Yes.
Okay. These are, whenever you see quadratics, think factoring. In other words, the solution lies in factoring the top. Is this bottom maybe x squared minus 3x? I'm betting.
Oh yeah, sorry. It's x squared minus 3x.
Okay.
My apologies.
No problem.
I did not see that.
Now, factor the top, factor the bottom, and then cancel where you can. I'll get this.
Okay. X plus 2. Right? Yeah, x plus 2 times x minus 1.
Okay. Bottom.
X minus 2 over x minus 1.
Okay. Now cancel. In other words, I can cancel that with that. And that's my answer. And I cannot simplify that any further. X plus 2 over x minus 2 does not simplify. So these kind of problems are all about finding linear factors that are the same, that you can cancel. There's only one difficult problem that you might run across, and that is something like this. What's that equal to? -1. In other words, the only time you can cancel is when they're identical, right?
Right.
Except when you have a minus b over b minus a. This is always the negative of that. So if I wanted to, I could write it as a minus b over the negative of a minus b. Notice that these two denominators are the same. Here, I'm pointing with my cursor, and I mean to be pointing with my mouse. Notice that b minus a is equal to minus the quantity a minus b. See that?
Right, okay.
Which means that I can always cancel, I can always cancel out the a minus b, and I'm left with -1. So the only other time that you can cancel stuff, other than when they're identical, is when you have this situation here, an a minus b over a b minus a.
Okay.
That's it. And I mean, I can't think of anything else. If I had x plus 1 over x minus 1, no. If I had x minus 1 over 1 minus x, yes, that's equal to minus 1.
Okay. Okay, right, yeah. That's a neat little trick.
Yeah, it is. And you'll only see it on the harder problems, and you may not even see it. But that's the hardest they get, where you can cancel and they're not exactly the same. And I've certainly seen a lot of problems like that. So it wouldn't surprise me if you get one on the test that has an a minus b over a b minus a.
Okay. So the next one is x cubed plus 5x squared plus 6x all over x squared minus x minus 12.
Again, what's the first word you should think of?
Factor.
Okay, factor the numerator. Always start with greatest common factor and then go from there.
X times x squared plus 5x plus 6.
Factor the denominator.
X minus 4 times x minus 3. Oh, plus 3, sorry.
Okay. Now factor the numerator further.
Oh, okay. It's so x times x plus 2 times x plus 3. Oh, okay. Right.
Now I put my denominator under there and you can see what can be canceled. Which means my final answer is x times x plus 2 all over x minus 4. Cannot do anything more with that.
Okay.
Okay? There's actually more to do with that, but I doubt that you'll ever see it. And that is, that's not the exact answer. The exact answer is n to x can never be equal to minus 3, as well as it can never be equal to 4. In other words, whatever domain restrictions were on that do not disappear just because I was able to cancel out the x plus 3. What it does is it produces what is called a hole.
Right.
It's not a vertical asymptote at x equals minus 3. It's a hole.
Right.
So you might have a curve that looks like this, and there's a little hole there.
Open dot.
Yeah, whereas that's completely different than a vertical asymptote. In other words, when I look at that final answer, I know I have a vertical asymptote at x equals 4, right?
Right.
But I also have a hole at x equals minus 3. Despite the fact that the x plus 3 canceled with that x plus 3 does not change the fact that x can never be minus 3. Because that would mean I'm dividing by 0.
Right. That is a no-no.
Yep, that's the first commandment. If you went on to Google and said 10 commandments of mathematics, you'd get 15 different lists. But every one of them would have the same first rule. Thou shalt not divide by 0. In fact, it kept Newton from releasing his discovery of calculus for 25 years. He discovered calculus in 1650, but he didn't publish until 1675 because he didn't trust calculus. The concept of calculus has a lot to do with dividing by zero. Not quite zero, but numbers that approach zero. In other words, you get calculus problems that look like this. Well, what happens to that as x goes to 0? Well, it becomes infinitely large. Okay? But nonetheless, that's how hard it is. I mean, it's really an amazing backstory if you think about it. Calculus is the greatest discovery in humankind. Math or science or otherwise. Calculus is the nuts. And here we have the greatest mathematician of all time, Newton, who was afraid to publish the greatest discovery of all time, calculus, because he didn't like this concept of dividing by super, super tiny numbers that approached 0. That's how much of a first commandment that is.
Funny.
Well, it's more than funny. It's really amazing when you think about it. From a historical point of view, he made the most important discovery in all of math history, certainly, and he was afraid to publish it for 25 years. In fact, in that 25-year period, he published Principia Mathematica, which is considered to this day to be the most important book on math ever. And it didn't include calculus, and he had discovered calculus by then. But he didn't put it in that book, and the book still was the most important book in the history of math.
That's fascinating.
It is, kind of. Yeah, to be able to go back in time and visit with Sir Isaac Newton. That'd be a fun thing. You know, especially knowing what calculus you know now.
Right.
All right, we got 4 minutes. Unfortunately, I have a 7 o'clock tonight, so I'm going to have to go at 7. We got 3 minutes. Got any last questions for tonight? I know we still have another session tomorrow, but...
I think I'm good for tonight.
Okay.
I'll work for tomorrow night.
I will talk to you then.
All right, Mr. Count. Thank you very much.
All right, William. Bye-bye.
Bye.